Okay, again, sample size was 12. The mean of the sample was 106. And the standard deviation was, I called it roughly 24. I rounded it. Okay, I'm taking license with that so I can work with this a little bit more carefully. Well, in order to find our confidence interval for the true population mean from mu, which is really what we want to know, well, I'm going to use the same formula again, x bar plus or minus the z for alpha over 2, okay, times the standard error. Okay, well, in this case, let's see, standard error is still going to be, it's going to be equal to sigma over the square root of n. I don't know sigma. The best I have is the standard deviation. That's all I have is standard deviation, okay, over the square root of 12, okay, which is, I think, 6.35, if I remember quickly. No, excuse me, was 3 let's see, 3 times 3, 4 times 4, 3.35, something like that. Close enough. Okay, over 24 is equal to roughly, I'm going to call this, would have been 8, so I'm going to call this about 6. Okay, so now the standard error is equal to roughly 6. Okay, now if I'm going to complete this formula, remember z represents the z-score that we need for a 2.5% error on one tail and 2.5% on the other tail. Okay, now alpha, that alpha represents the amount of risk of error that we have. If I went far enough out, if I decided to go out 3 standard deviations instead of 2, then the probability that the true population mean would be outside of that range shrinks just as that area outside the curve shrinks. Then it would only be like a tenth of a percent between the two, a tenth of a percent here and about a tenth of a percent there. Okay, it's going to be much smaller level of error. If I went out 4 standard deviations on either side, there'd be almost no error. But my confidence interval would be so wide that the data might not even really be that useful to me. Okay, so 6.35, is that what that is? Okay, so at any rate, so now I'm going to look at this. I'm going to say to myself, okay, now Z, this works for me. The Z table works for me when you know the population standard deviation. The problem is I don't know that. I'm using the standard deviation of the sample to approximate it. So just like the mean has a certain amount of error built into it, now my standard deviation and my spread has a certain amount of error built into it. I have to accommodate for that error. So now in order to accommodate for that error, instead of using the Z table, I use a T value instead. So I'm going to call this X bar plus or minus T for alpha over 2. Okay, and alpha again, alpha in this particular case is 0.05, so alpha over 2 is a tail that gives you 2.5%, times the standard error. Well, now let's take a look at the T table and take a look at what that looks like. Okay, let me go back here. Okay, and open the T table. Okay, here's our T table. Okay, and what we see here with the T table, our confidence interval or confidence level for 95% means a T table with a right tail or left tail. They could have said left tail just as easily, but it's because it's symmetrical. Probability of 2.5% represent 95% confidence interval because we're allowing for error in both tails, two-tailed. Okay, so now if I look at this, the degrees of freedom represents my sample size minus 1. If my sample size is very, very large, look what the t value is. It's 1.96. It's the same as the standard deviation is. But we notice that as we get a smaller and smaller sample size, the t value that gives us that result, the t distribution that gives us that result, that confidence interval gets larger and larger and larger. And it gets larger so the confidence interval spreads out in order to accommodate for the uncertainty that we have in estimating the standard deviation because our sample size is getting smaller. So in our particular case here, we have a sample size of 12, so 11 degrees of freedom. So instead of using 1.96, we're going to use 10, 11. We're going to use, let's see, here we go, 2.2, 2.201. In the right spot there? Yep, 2.2. Where are we? 11, 2.201. That value right there. Okay, 95% and 11 degrees of freedom. So we're going to use 2.2 instead of 1.96. That's going to make our confidence interval wider and make up for that uncertainty that we have because we don't know the true population standard deviation and because it's such a small sample. So we got 106 plus or minus 2.2, I'll round it to that, times 6.35. Okay, so that's going to be 106 plus or minus, and we do our calculation, 2.2 times 6.35 equals 15.87. Okay, and let's see, we got 106 minus that value is going to be, oops, 90.12, and I'm going to go back and say 106 plus that value. It's going to be 121.9. Okay, that's my confidence interval. Now, let's talk about this for a second. The value that I put into memory here, the value that I put of that 15.87, you remember I got that by multiplying the t-score that I need for an alpha of 5% or a right tail or a left tail of 2.5%. I got that from my t-table. It turned out to be 2.2. And my standard error for my sample was 6.35, which I'm using to approximate the population standard deviation. And I get a number at 15 that I add and subtract to my value 106, what I think, which is my sample mean, but I think approximates, I'm hoping approximates the population mean. Okay, so what do we call this value that I'm adding and subtracting to my estimate of the mean? You guys know what that thing's called? Okay, think about think about if we're just looking at election polls and stuff like that, and they would always tell you, oh well, so and so has 49% of the vote, plus or minus 3%. It's a margin of error. Exactly that number that we're adding and subtracting, the t-score times the standard error, is called our margin of error. In other words, that's the amount of error that we're willing to accept, that we expect that we're expecting above and below that particular number that we're estimating to be the mean. Okay, so that's our margin of error. So now we're going to keep that in mind because that's going to come up later on. So now, if I asked you what the point estimate was for this particular sample, what would you say the point estimate is? Okay, speaking of our statistical glossary. Right. Point estimate is the mean. That's the one point that we're saying that we are predicting approximate the population means. That's a point estimate. Okay. Our confidence interval is a range from one number to another number. And our confidence interval is basically that point estimate with the margin of error added and subtracted from it. Okay, so we're a little bit more comfortable with those terms, hopefully. And if they get used on the test, we'll know what they mean. Okay, so now I'm going to go to another example now that involves, instead of numbers where you're actually working with means, numerical values and means, we're working with proportions. So I'm going to start with a new page. Okay, and I'm going to pull up a new example, I think, too. I think the second problem in that collection of examples will help us out here. Let's see if I can't find it. Here we go. Okay, let's see if we answered these questions. What's the point estimate of the blood glucose level? Well, we know that that's the mean. What's the margin of error? We know how to calculate that, the t-score times the standard error, and the 95% confidence interval. We figured